Hello friends, welcome to our channel. In previous video we discussed about clause sets and their definitions. In today's video we will discuss some results based on clause sets and derived set in a metric space. Theorem. In a metric space, XD, a subset of capital X is closed if and only if its complement is open. Is open. Or a subset f of capital X is closed if and only if f contains all its limit points. That is, d of f is contained in f. The derived set of the subset f is contained in f. Proof. In the given theorem, first, in a metric space XD is a metric space, a subset of the metric space is closed if and only if its complement is open. Is the definition of clause sets. One more definition of clause set: a subset f of x is closed if and only if it contains all its limit points. We will prove both. Let capital F be a closed set. Of capital X, then by definition of closed subset, F contains all its limit points. We prove that F complement is open. Suppose F complement is equal to 5, then there is nothing to prove, because empty set is always open set. Suppose F complement does not equal to 5. So there exists X is belongs to capital X such that X is belongs to F complement. This implies X does not belongs to F. The rectangular part shows the metric space X. This circle represents F. X belongs to F complement. Suppose X, small x is here. So X does not belongs to capital F. This implies X is not a limit point of capital F, because capital F is closed. So capital F contains all its limit points. So by definition, of limit point, there exists R greater than 0 such that sphere centered on X with radius R intersect with F minus X is equal to 5. This implies SRX intersect with F is equal to 5. This implies sphere centered on X with radius R contained in F complement. So X belongs to SRX contained in F complement. This implies F complement is a neighborhood of X, but X is an arbitrary point of F complement. Therefore, F complement is neighborhood of all its points. This implies F complement is open. Conversely, suppose F complement is open. We have to prove that F is closed. That is, F contains all its limit points. Suppose X be a limit point of f such that X does not belongs to f. This implies X is belongs to f complement. This implies there exists r greater than 0 such that sphere centered on X with radius r is contained in f complement, because f complement is open, so it is neighborhood of all its points. Therefore f complement is neighborhood of X also. So sphere centered on X with radius r is contained in f complement. This implies sphere centered on X with radius r intersect with f is contained in f complement intersection f, which is equal to phi. This implies sphere centered on X with radius r intersect with f is equal to phi. This implies X is not a limit point of f, a contradiction. Because X is limit point of f. This contradiction shows that our supposition is wrong. Therefore, X is belongs to f, but X is an arbitrary limit point of f. Thus, f contains all its limit points. This implies f is a closed set. Hence, f is closed if and only if f complement is open. Next theorem. In any metric space XD, each closed sphere is a closed set. Proof. Let XD be any metric space and SRX be any closed sphere, we have to prove that SRX is closed set. That is X minus SRX is open. If X minus SRX is equal to phi, then there is nothing to prove, because empty subset is open. This implies X minus SRX is open. This implies SRX is closed subset of capital X. Suppose X minus SRX does not equal to phi. Let A is belongs to X minus SRX. This implies A does not belongs to SRX. This implies distance between A and X is greater than R. We see graphically the rectangular part is the metric space XD. Sphere centered at X with radius R, SRX, in which boundary points are also included. Therefore, SRX is closed sphere. A is belongs to capital X such that A does not belongs to SRX. So suppose this is A. Now distance between A and X is greater than R. Distance between A and X is greater than R because this distance is R. This implies dAx minus R is greater than 0. Suppose dAx minus R is equal to R1. This part is R1. We have to prove that sphere centered on A with radius R1 is contained in X minus SRX. that is x minus SRX is neighborhood of A. Let y is belongs to sphere centered on A with radius r1, then distance between A and y is less than r1. Equation number 1. Now by triangular inequality, we have distance between A and x is less than equal to distance between A and y plus distance between y and x. This implies distance between y and x is greater than equal to distance between ax minus distance between ay. This implies distance between y and x is greater than distance between ax minus r1, because by equation 1. This implies distance between y and x is greater than r, because r1 is equal to dAx minus r. This implies y does not belongs to sphere centered on x with radius r. This implies y is belongs to x minus a sphere centered on x with radius r, but y is an arbitrary point of S R1A. This implies sphere centered on A with radius r1 is contained in x minus SRX. This implies A belongs to SR1A contained in x minus SRX. This implies x minus sphere centered on x with radius r is neighborhood of A, but A is an arbitrary point. This implies x minus SRX is neighborhood of all its points. Therefore, x minus SRX is open set. This implies sphere centered on x with radius r is closed subset of metric space XD. Hence, in metric space, every closed sphere is a closed set. Next theorem. Let X be a metric space then any intersection of closed sets in capital X is closed. Proof. Let F1, F2, F3 and so on be the collection of closed subsets of capital X that is F lambda. Lambda belongs to indexing set. We have to prove that intersection F lambda, lambda belongs to indexing set, is also closed. Let capital F is equal to intersection lambda belongs to indexing set M lambda. To prove F is closed, it is sufficient to prove that F complement is open. Now, F complement is equal to X minus F, which is equal to X minus intersection lambda belongs to indexing set F lambda. We can write it as union lambda belongs to indexing set X minus F lambda, because by De Morgan law. As F lambda belongs to indexing set are closed for every lambda, this implies F lambda complement is open, that is X minus F lambda is open. We know that arbitrary union of open sets is again open. This implies union lambda belongs to indexing set F lambda complement is open. That is, union lambda belongs to indexing set X minus F lambda is open. This implies F complement is equal to union lambda belongs to indexing set X minus F lambda is open. This implies F is closed. That is, arbitrary intersection of closed sets is closed. Next theorem. Let XD be any metric space, then finite union of closed sets is closed. Proof. Let capital XD be any metric space. Suppose F1, F2, F3 and so on, Fn are closed subsets of capital X. We have to prove that F1 union F2 union F3 union so on union Fn is closed. Let capital F is equal to union I varies from 1 to n Fi. To prove F is closed, it is sufficient to prove F complement is open. Now, F complement is equal to union I varies from 1 to n Fi its complement. This implies F complement is equal to intersection I varies from 1 to n X minus Fi now Fi is closed for every I varies from 1 to n. This implies x minus fi is open for every I varies from 1 to n. We know that finite intersection of open sets is open. This implies intersection I varies from 1 to n x minus fi is open, that is f complement is open. This implies f is closed. Hence, finite union of closed sets is closed. Next theorem. Every derived set is a closed set. Proof. Let XD be any metric space and A be the subset of capital X, then D of A be its derived set we will prove that D of A is closed, that is D of A contains all its limit points, because we know by the definition of closed sets, a set is said to be a closed set if it contains all its limit point. So if we have to prove that D of A contains all its limit points, then D of A becomes a closed set. Let small x be any limit point of D of A. We have to prove that X is belongs to D of A. As X is limit point of D of A, so there exists R greater than 0 such that sphere centered at X with radius R intersect with D of A minus X does not equal to phi. This implies there exists at least one point A belongs to SRX intersect D of A such that A does not equal to X. This implies A belongs to sphere centered on X with radius R and A belongs to D of A. Put it equation number 1. Graphically we see rectangular part is a metric space X with metric D. Sphere centered at X with radius R. A belongs to SRX. That is this point A. Then distance between X and A is less than R. This implies R minus distance between X and A is greater than 0. Let R minus distance between A and X is equal to R1 is greater than 0. We have to prove that sphere centered at A with radius R1 is contained in sphere centered at X with radius R. Let Y belongs to sphere centered at A with radius R1. This implies distance between A and Y is less than R1. Now, by triangular inequality, distance between Y and X is less than equal to distance between Y and A plus distance between A and X is less than R1 plus DAX is less than R. This implies Y belongs to sphere centered at X with radius R, but Y is an arbitrary point of SR1A. This implies SR1A is contained in SRX. This implies SR1A intersect with capital A is contained in SRX intersect with capital A. This implies SR1A intersect with A minus A contained in SRX intersect with A minus A. but sphere centered on A with radius r1 intersect with A minus A does not equal to phi, because A belongs to D of A, that is A is limit point of capital A. This implies sphere centered at X with radius R intersect with A minus X does not equal to phi. This implies sphere centered at X with radius R intersect with A minus A does not equal to phi. This implies X is a limit point of capital A. This implies X is belongs to D of A, but X is an arbitrary limit point of D of A. This implies D of A contains all its limit points. Thus, D of A is closed set. It is sufficient for today. In the next video, we will discuss some more results on derived set and subspaces of a metric space. So keep in touch, watch our videos and subscribe our channel for more and more videos on these topics. Thanks to all. Have a nice day. Bye bye.